like 2 meters by 2 meters. And we have areas that are like, let's say 4 meters. So this is going to be 4 meters. And then this is going to be 4 meters. And let's assume these are right next to each other. There's not like a space between them. No, that's what. Sorry about that. And this can be E equals like 3 Tesla, obviously in positive Z. And then B2 equals, let's say 5 Teslas. And the negative Z. Can everyone see that? Try to zoom in.
I'm gonna zoom in like unless you're gonna be doing work.
Oh, that's
zoom in, but a little bit. Yeah, that's good.
There we go. That's better. Okay. So we're gonna assume this thing goes in this direction to the right. Obviously, it's the other way would make sense. So, and he's probably gonna give you some velocity, like velocity equals like 1 meter per second. So this thing's going to the right at 1 meter. So, let's just say he'll probably ask something like, what, let's see, he says, what is the direction of the induced current over this period? Okay, what over the period of time, what is the magnitude of the current? And I have no idea what he's asking out there. So, let's just say it's going to the right at 1 meter per second. So, between time 0, t equals 0 to t equals 2, that'll be the time where this loop here is going from not in the magnetic field at all to completely in the magnetic field. So everybody understand why? Because it's 2 meters long. Okay, cool. Good stuff. So, if that's happening, what is our change in flux? I don't have a calculator, so you're going to have to help me out. So, our V induced is going to equal our change in flux over, negative change in flux over change in time. And so that's going to equal negative. Our final flux is going to be, what is it? Something K.
I don't know. Do you want me to look it up?
I don't have a calculator, so I'm gonna.
Oh.
I'm not gonna do it all. I'm just kind of.
I can get you a calculator.
Give me my notebook too. Anybody? What's the final flux? What was the equation for flux? That will help.
Magnetic field times area.
Okay, so magnetic field times area times like cosine of the angle or something. So, and that's when they're parallel or not parallel. When they're perpendicular, that angle is actually supposedly 0. Okay, thanks. So I'll put over here blah 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 flux equals BA cosine of. But in this kind of problem, your cosine of theta should always equal 1. So B is 3. So you have 3 Teslas times your area, which is 4 meters squared, and then minus 0 because our initial flux was 0 because we had no magnetic field. Cool. Our change in time was 2 seconds. Awesome. So, our V induced equals negative 12 over 2, which is like negative 6 volts. And remember, he always asks for the magnitude of these forces. He's never going to put something like 6 volts on there. That just doesn't make sense because you can't get negative voltage. So, what it means when you have negative 6 volts means it's indicating a certain direction. And I can't remember which direction that is. But we can figure that out. So, what will be the direction of the current if we're going into this positive Z magnetic field. Yeah, right hand rule. Remember the right hand rule.
For which side of the thing? For which side of the?
Oh no, it's the current induced in the thing. Yeah, should be clockwise. Yes, it should be clockwise. So if you remember, yeah. So the change in flux is towards the positive Z direction, which means flux always opposes the change in magnetic field. So if the magnetic field that's changing is going out, you have to oppose that and have it be going in, and so that means direction would be clockwise. Okay? And so in this case, this just means 6 volts in clockwise direction. So, oh yeah, he also needs to give like a resistivity. So your resistivity is going to equal something like 8 meters. I'm just gonna say
5 million ohms.
Yeah, that makes sense. That's just we're just gonna say it's gonna be like 0.5 ohms. Wow, that's a terrible ohms per meter. Squiggly line.
It's kind of cute. It's like a little, yeah, it looks like
You're gonna have half the octopus per meter, so I don't know what that means, but yeah. So, your current that's induced is going to equal your V induced divided by your R, and then R equals your resistivity times length. So that means your I induced equals 6 volts divided by your resistivity, 0.5, times your length, which if you find the perimeter would be 8 meters. And you end up with 6 divided by 4, which is 3 halves. 3 halves amps. Cool, good stuff. Hope I haven't messed anything up yet. Oh, nice. Got it just in the right spot. Okay, so now we found one good thing here. 3.5 amps. That's one of the questions. Yeah.
With the current fluid direction, the induced current be the same?
Yes. Yeah. The current. Yeah. You technically voltage doesn't have direction. I don't think. Yeah. You don't. I just when I mean. Yeah. When I meant that, it should be current. Sorry. Yeah. L is length. Length of the loop.
Length of the entire loop.
Yeah, length of the entire loop. So yeah, that just means the perimeter in this case, which is
the perimeter is square.
Yeah, exactly. Yeah, the length of the entire wire. In this case, the loop is 8 meters long. Yeah, sorry if I didn't explain that. Yeah, so that's how he did that in that one problem in class. So yeah, resistivity. He's always gonna give a resistivity, or in what he more truly explained it as indicated resistance per unit length, because resistivity includes the area of the wire. But as I remember, I think she pointed out sometime. Yeah, so he's just gonna give you something in like ohms per meter, and then you just multiply that by the entire length of the loop to get the resistance of that loop. And that'll be pretty simple. So you just have to remember this equation would be good to remember, this equation is good to remember, this equation is good to remember, and that equation is good to remember. Definitely remember all of those.
He's not going to give you equations, so
yeah,
make sure you memorize them.
I don't think he's giving you equations in any of the tests so far. So yeah, hint, hint, these equations would probably be good things to write down. Cool, so that was important because we had the magnitude of the current. So the magnitude of the current, which was question number 2, is 3/2 amps. The direction of the current was clockwise. That wasn't also important. And then the third part, which of the following would have an effect of increasing the magnitude? Oh, I have no idea. I don't even know how to give you a question on that.
What?
Which of the following would have the effect of increasing the magnitude on the induced current?
It'll probably be something like changing the magnetic field direction.
So it's probably going to be something like increasing the area of the loop, or decreasing the area of the loop, or like increasing the magnetic field at, increasing B1 to 4 teslas. So if you increase the magnetic field of B1, would the induced current have a stronger, would it be a stronger induced current, have a greater magnitude if you increased B1? Yes, because your flux will change more. What if you increase the area of the loop? Also increase magnitude, because remember, just look at this equation. So increasing your flux, so if you increase B or increase A, you're going to end up increasing the change in flux, right? What if it took 4 seconds instead, like the velocity was half a meter per second? What about then? Would it increase or decrease the magnitude? I hear mumbles. That doesn't count. Decrease. Thank you. Yes, because your change in time is now greater. You would have a smaller current. Cool. What if you increased resistivity? I don't know how that would happen, but if you increase this number here, what would happen? Yeah, it'd be a decreased current because your resistance increased. So if you're having problems with those, just go through all of these variables: B, A, T, resistance, basically all of those, and just think, if this increased, what would happen to the current? Yeah.